So like I said, this is the last section of chapter 3. So we're still talking about uses of radian measures in our trigonometry. Next chapter starts talking about the graphs of sine, cosine, and tangent. So we'll be graphing these functions on like a regular XY plane. But to finish up chapter 3, we're going to discuss linear and angular speed, which is an application of these two of radian measures. So linear speed is different than angular speed. Suppose that a point P moves at a constant speed along a circle of radius r at center 0, so at the origin. The measure of how fast the position of P is changing. So for linear speed, I'm going to make this one green. Linear speed is measuring how fast the position of P is changing. This is linear speed. So we're saying how fast is this P changing as we move around the unit circle? So the distance or how fast point P is changing. That means we're looking up speed. That means that it is going to be distance divided by time, or V equal to S divided by T. And remember, S for us stands for arc length. So when I'm asking you to find linear speed, we're straight up talking about how fast that point P is moving around the circle. Again, S is the length of the arc, and T is time. I can also ask you, using the same picture, not how fast P is moving, so looking at this point P, I can also ask you for angular speed, which is measuring something different. As point P in the figure moves along the circle, the ray OP, so we're talking about this ray right here, OP, rotates around the origin. Because this ray is the terminal side of the angle, POB, this angle right here, the measure of how fast the angle is changing is called angular speed. So again, how fast the angle is changing is called angular speed. So this time I'm looking at this moving around. Angular speed is going to be symbolized by the Greek letter omega. It looks like a W, but it is an omega, lowercase. So omega is going to be equal to theta divided by t, where theta is your angular radians. So that is angular speed. So we have linear speed and we have angular speed. Two different questions with two different types of inputs, two different types of units at the end. As with earlier formulas in this chapter, for angular speed, theta must be measured in radians. We cannot do this formula in degrees. It only works in radians. That means that omega is going to be units-wise expressed in radians per unit of time. So like radians per second, radians per minute, radians per whatever. That's how we're going to express omega. So instead of like velocity, we're used to miles per hour. This would be like radians per hour. We're measuring something different. So to kind of keep it all together, this is going to be really important for you, this little yellow box. These are your formulas for angular and for linear speed. So for angular speed, that was what I did in purple. This is omega. We said that that formula was theta divided by t. So we can look back, we can find this formula really quick. For linear speed, there are multiple variations of the formula depending on what you're given. What we wrote down in the notes was the velocity, linear speed, is equal to arc length divided by time. Remember, S is arc length. But let's say I'm not given exactly the arc length. I do have a formula for arc length, and when we did the formula for arc length, we said that this was r times theta. So we can rewrite the velocity formula as maybe just r times theta. It's still arc length. I'm just showing you different variables that still multiply together to create arc length, which may change what you're able to do. But what's really cool is if you notice theta divided by t. Didn't I just write down a formula for what theta divided by t is? No. What is theta divided by t? Yeah, what's this letter called though? Oh, not W. Omega, which means we can rewrite the velocity formula as r times omega. So we can relate our angular velocity and our linear speed, sorry, I said velocity, angular speed and linear speed with this last formula. The reason I gave you a bunch of different derivations or versions of this formula is because depending on what you're given, you'll have to use varying different derivations of this formula. If you're given straight up arc length, you're going to use this one. If you're given a radius and a theta, you're going to use this one. If you're given the angular speed, you're going to use this one. So you have to choose which formula is most appropriate for your problem and then pick it off of this table. These will start to show up on your formula quizzes, by the way, because we got to have these memorized. I know. Okay, let's see some examples with them just to see what's going on. Example 1. It says, I think my papers are out of order. Oh, they are. Not bad. Suppose that point P is on a circle with a radius of 10 centimeters, and ray OP is rotating with an angular speed of pi over 18 radians per second. Just from the given part of this question, I know that I was given R is 10 centimeters, and I was given omega, and that omega is pi over 18 radians per second. For the rest of this problem, for A, B, and C, I can use this information in the given to solve my questions. Part A says, find the angle generated by P in 6 seconds. So what letter am I looking for here if it says find the angle? Theta. So I know my goal is to find theta. What other piece of information am I given? 6 seconds. I'm given time as 6 seconds. Okay, I need a formula that uses theta, r, omega, or t. So we're looking back at our formulas here. Is there a formula you have that uses all of the letters, some of the letters, but so much so that we only have theta being missing? All right, so I need a formula from the front page that uses either r, omega, theta, and time to relate these things together. V equals r theta over t. Yes, but we don't, and that if we use that one, so if we use V equals r times theta over t, I don't know this one, and I don't know this one. I'm looking for a formula where I only don't know one thing. Yeah, that's the one I'm going to want to use here. This is going to be omega. Let's see, that's blue. What color did I use? That means I'm going to use the omega equal to theta divided by t. Yes, it gave me an r as well. Is that the right formula? Yes. It gave me r as well, but I only need to use a formula where there's one unknown. In this formula, I only don't know theta. So let's solve for theta. If I rewrite this formula so it says theta equals, means deriving the formula, I could multiply by t on both sides and I'd have theta equal to omega times t. That's the derived formula for theta. At this point, we just plug in what we have. What is omega?
Pi over 18.
What is t? So 6 pi divided by 18, when you multiply those together, that means that this is pi over 3. So my theta is pi over 3, and this radians. Just so you make sure you know what you found, let's put units on things today. I don't think your homework requires that, but I think it would be helpful to make sure you know what we're finding. So the trick with this, kind of like if you're taking physics, at least back in the day they taught physics like this, you write down all the variables you have, you try to find a formula where there's only one variable you don't know. That's the formula you're going to use to relate all those variables together. Can we try another one? Okay, so this problem says find the distance traveled by P along the circle in 6 seconds. The distance traveled, not velocity, the distance traveled by P along the circle, that means I'm asking for the arc length. And I was given time again. Now don't forget, I still have R and omega from the beginning of this problem, from the given. Is there a formula that we have that relates S, R, omega, or T, where there's only one variable? And this is kind of a trick question because it's not even on these notes, but it was answered on your formula quiz. What is the formula for arc length? S equal R times theta. Well, in this formula, the only thing I don't know is S, because I know R, and I actually know theta from this answer right here for 6 seconds. So if I fill in everything that I know, it told me that the radius is 10 centimeters, and I know that at 6 seconds I have moved pi over 3 radians. Again, that's from here. Beep. Because we're still at 6 seconds. So, okay, 10 pi divided by 3 would be the simplest form for radians if I left it in terms of pi. But let's say that this question wanted it not in terms of pi. We would actually press 10 pi divided by 3 on our calculator. And this would approximately give us 10.4720 centimeters. Since this is a distance, it makes more sense to put it in a decimal form than in terms of pi, just because if I say, please cut me a piece of paper that's 10 pi over 3 centimeters, you'd be like, how long? But if I say 10.47 centimeters, you'd be like, okay, got it. So it's a more clear way to answer a question when it comes to arc length. Okay. One more time, we're going to find this time linear speed of p in centimeters per second. So I know that I want to find linear speed. This is what I need to find. The only things in this problem, because it doesn't say in 6 seconds, the only things that I know are r and omega. Is there a formula that relates the velocity, r, and omega? Yeah, it's the velocity equal to r times omega formula. Because in this formula, the only thing I don't currently know is your linear speed. So if I fill in everything I have, the radius is still 10 from the given. The omega is 18 over 10. So 10 pi over 18. We'll reduce that one just because it does reduce. So it would be 5 pi over 18 centimeters per second, which is a weird way to answer the question. So if we actually take that out of terms of pi, just in case that's what the problem's asking us for, it would be approximately 0.8727 centimeters per second.
Why did we do 5 pi over 18 and not 5 pi?
It should be 9. That's just a math mistake. Thank you. Yep. I'm going to blame that on it being Friday. So again, these are all equivalent expressions, just depending on how I want your answer written, or by I want your answer in, I mean your textbook. So the key here with these kinds of problems is, one, remembering all of the formulas, which is why I'm having you memorize them, and then picking the correct one that applies to your problem. So I like to list out the variables I have and the variables I want, and seeing which formula gives me all of the information. In example 2, we have a nice pulley system here. So this is a rope. In case you've never seen a pulley system, this is not a CD. Okay, it's not like a record. This is a pulley, so this is a wheel that this rope, I guess, is tied around, and so you can like pull things around with it. It's a pulley system. A belt runs a pulley of radius 6 centimeters, so here's my 6 centimeter radius, at 80 revolutions per minute. It says find the angular speed of the pulley in radians per second. Okay, let's think about what they gave us. They gave us in this problem that the radius is 6 centimeters. I like to just write it out. I know it says it right there, but I like to write it out so I know I was given that information. That's this bit right here. Cool. What is this? 80 revolutions per minute. Is that theta? Is that arc length? Is that time? Is that, like, what is it? Time would be something measured in minutes or seconds. This is measured in revolutions per minute. Theta would be measured in radians. This is revolutions per minute. We're going through all of them. Arc length is a distance, so it would be like centimeters. What's left? Omega. It is omega. This omega is 80 revolutions per minute. Earlier in the notes, I said that omega would be measured in radians per unit time. It could also be measured in revolutions per unit time. But this question, part A, wants us to find angular speed, which is omega, but change it in terms of radians per second, back to what's normal for us. So we need to take the number they gave us for angular speed and just change the units. Because I have angular speed, it's just in the wrong units. So we're just doing a bunch of conversions here. We're going to take omega, which we wrote to be 80 revolutions per 1 minute, revolutions per minute, and we're going to convert it to radians per second. First things first, let's get it in terms of seconds. I know that to do conversions, the units need to be across from each other so they will cancel out. If I say 1 minute, how many seconds is that? 60. So if I do this, that means the minutes are canceling out. And if I were to just do 80 divided by 60, I'd be measuring in revolutions per second. Not what I want, though. I want radians per second. So I need that revolutions to cancel out. So in 1 revolution of a circle, how many radians do I have? 2 pi radians. So at this point, the revolutions would cancel out, and the units that are still showing would be radians per second, which is what this problem wants and what we normally measure omega in, radians per second. So all of this to say, what you are putting in your calculator is the numbers that are left. You can ignore the ones because multiplying by 1 does nothing. You are putting 80 times 2 pi divide by 60 into your calculator or into your brain. This one's easy to do in your brain because 80 times 2 is 160. And then those both have a 0, so we can get rid of the 0. I'm just doing this the easiest reduction possible. 16 and 6 are both even numbers, so I can divide by 2. This ends up being 8 pi divided by 3 radians per second. Since I'm measuring something in radians, I leave it in terms of pi. Okay, pause because I hear murmuring, which means we have questions. What are our questions? Please ask. I love questions.
Where did 2 pi come from?
In 1 revolution of a circle, so like if this was a unit circle, if I go all the way around, that's 360 degrees, or how many radians? 2 pi.
Wait, so how do you know it's 360 degrees?
A revolution means all the way around.
So how do you know it was like twice?
What do you mean?
I meant like.
The 2 pi?
So what does the 80 mean? The 80 revolutions. Like,
They gave me that one.
okay.
Yeah, that was given to me. So that means like this pulley, if I put a little dot right like at the end over here and measured for a minute, it would circle this thing 80 times. So it's doing 80 revolutions every minute.
You said 1 revolution is like 360
Degrees, which if we're measuring in radians, is 2 pi radians.
Okay.
Yeah. Is that clearer? Clear as mud. Cool. Okay, part B here goes on to ask you to find the linear speed of the belt in centimeters per second. So I'm glad we changed the to per seconds, which is why we had to do this, because we want per second, not per minute. And if we're looking for linear speed, that means that I am trying to find linear speed. I was given R and I was given an omega. Is there a formula that relates linear speed to radius and angular velocity? Okay, so that means that this formula should be, switch color pens, linear speed equal to R times omega. What is the radius? 6 centimeters. And the omega? 8 pi over 3 radians per second. So when I multiply centimeters times radians per second, I end up with centimeters per second. 48 pi divided by 3 is 16 pi, because 48 divided by 3 is 16. So that would be 16 pi centimeters per second, or if you change that to a decimal, 16 times pi is 50.2655 centimeters per second. Just depending, again, on how the question wants, either in terms of pi or rounded. Okay, last application in our notes for this unit. Example 3, finding linear speed and distance traveled by a satellite. So a satellite traveling in a circular orbit, 160 kilometers above the surface of the Earth. So here's my 1,600, I said the wrong number earlier, kilometers above the surface of the Earth. Takes 2 hours to make an orbit. An orbit is a revolution. The radius of the Earth is approximately 6,400 kilometers. So in my picture, that's what's happening here. We're going to approximate the linear speed of the satellite in kilometers per hour. Let's figure out what we know so far. Number 1, we do actually know the radius of the satellite. What is the radius for the satellite?
6,400 kilometers.
Ooh, that's the radius of the Earth. So going all the way out to the satellite, you just add those two numbers together because you have the radius of the Earth plus the distance that that satellite is traveling above the Earth. That means that my radius is 8,000 kilometers. Cool. The other thing it told me is that it takes 2 hours to make an orbit. What did that give me if they told me 2 hours to make an orbit?
Omega.
It told me omega. So the omega is, did I just write down the wrong?
2 hours per revolution.
Yes, sorry. 2 hours. Wait. Okay. They told us that it takes 2 hours to make 1 revolution. What am I trying to say out loud? Hold on. Okay. I've got words in my head now. They told us that 1 revolution takes 2 hours because omega is always revolutions per time unit, not time per revolution. Okay? But omega should be measured in radians per minute, per hour in this case. So instead of revolutions per hour, I need to get that revolutions to go away. So just like before, how many radians in a revolution? 2 pi radians. So the revolutions would cancel out, and I have radians per hour. I don't need to change this to minutes or seconds because the question does ask per hour, so I don't have to change the unit of time. So that means I'm multiplying 2 pi, or dividing 2 pi divided by 2, which is pi. So my omega is pi radians per hour. This is what I was trying to say down here and did it super wrong. So they gave us R and they gave us omega.
So omega has always been measured in time per what?
So it should be either revolutions or radians per time unit. It depends on the question of whether I want it seconds, minutes, hours.
So revolutions
Per unit of time. So if they give you a time, you have to put that in the denominator because time is your per time.
So it's revolutions by time.
Correct, yes. And translating it to radians per time is the goal. Whew. Okay, now the question here was actually asking for linear speed. We have a formula for linear speed that relates radius to omega since that's the only two things we have. We know that linear speed, switch colors, should be equal to R times omega. So if we fill that in, the radius was 8,000 kilometers, and omega is pi radians per hour. which means 8,000 pi kilometers per hour. Or if you multiply that out, it is 25,132.7412 kilometers per hour. That satellite is booking it, which makes sense because they're moving really fast out in space. I hope they're moving fast, or else they will fall into gravity and all that business. Science, baby. Okay.
Miss Quigley, isn't angular speed how fast it looks like it's moving?
Angular speed is how fast the angle is changing. And linear speed is like how fast, like when we think about speed in a car, that's linear speed. Or
Does it say angular or linear?
It will, yes. Yeah.
So we don't have to figure it out.
I don't think so. I don't think there's any trick like that. Part B asks you to approximate the distance that the satellite travels in 4.5 hours. Ooh, distance. Not speed, but distance. So let's think about this. The things we know so far in this scenario, I'm just going to list them out again so we know this. We know the radius, check. We know omega, check. And now we just found the linear speed. We were also given that the time is 4.5 hours. I need to find a formula on my page that relates distance to one or all of these formulas. What variables? My words are messing up today. Is there a formula you can find that involves distance and some of these variables?
Can we just use the regular linear speed?
Okay, great idea. If we use regular linear speed, you're talking about this one?
Yeah.
Which one is distance?
S.
S is distance. My arc length is the distance that we have traveled around. My arc length on the edge is the distance. So if we're trying to find S, we can derive this formula so that it says S equals. That means this would say S equals to V times T, linear speed times time. Well, we just found that the linear speed, and I'm going to use the not rounded version so I can save myself a rounding error, 8,000 pi. We know that the time is 4.5 hours. Good thing we left our speed in kilometers per hour since I was given an hour. So we would calculate at this point. 8,000 times 4.5 is 36,000 pi kilometers, which is approximately 113,970.3397. I said that number wrong still. 55 kilometers. Yowza. So again, the key with these problems, because they're all sort of different, is to figure out what you know, what you want to know, and pick a formula that relates them together with only one thing missing so you can solve for it. This is also a great physics skill, my physics friends. Find what you know, what you want to know, and relate them together with one missing thing. The thing that might trip you up is your conversions, so make sure you read the problems to know how you're converting them, if you're going all the way to minutes or seconds, or if you're staying in hours, because you will have to convert them. Because I assume there will be questions on this unit, since it is a little bit confusing because it's so detailed with the units, we're going to spend the rest of the class working on homework. I'd prefer you start with this one, even if you haven't done some of the other ones. That way I can answer your questions about this unit while we're here. And that is that.